So welcome everybody. So over the last few days, we've seen this in two kinds of results. Mostly of the first kind, where you prove a theorem about an algorithm, and that's the result. And there's been some tension between that and things you can actually implement. That tension is an ongoing theme of the program, and one of the goals is to find some way to find algorithms that have both those things. And the theme of today's morning talks is that, more talks that bridge theory and practice. And our first speaker is Oded Schwartz, who's a program organizer, who will tell us about practical fast matrix multiplication.
Thank you, Nikhil. All right, so this is a joint work of many people, so thank you. And matrix multiplication is everywhere. I will motivate only very little why we should multiply matrices. Let me just remind one motivation, and that is the huge cost of matrix multiplication. So OpenAI spends more than half of its budget on compute, so training and inference, and that is mainly matrix multiplication. And as Sam Altman said, we will have to monetize it somehow at some point. Compute costs are eye-watering. And it also has an environmental severe impact. So in next year, the cost of compute is going to cross the 1% of global electricity. And I think in the US, it's more than 4%. So out of that, depending on estimation, anything between 45 and 90% is matrix multiplication. We have many state-of-the-art implementations of both software and hardware for matrix multiplication on GPUs, on CPUs. We have accelerators, Tensor Core or on NVIDIA's GPUs and other accelerators. Practically all of them are based on the classical cubic time algorithm, the n-cubed algorithm. Although we do know that we have Schwartz's algorithm and many others. So why is that? Why are we still a few decades back? Just a quick reminder from Olga's talk. So Schwartz showed us how to multiply matrices faster. You take linear combinations of the A matrix, 2 by 2 matrix, a linear combination of the B matrix, multiply them pairwise, do some extra linear work, and you get the results, and you can apply this recursively. So you think of each element here as a block, and then addition and subtraction are just addition and subtraction of matrices, and multiplication is a recursive call. And then you get the nice recursive formula, which gives you n to the log base 2 of 7 arithmetic cost. What you see here is a graph representation of the same computation, so the arithmetic circuits. These are the inputs. These are the linear, the UV matrices represents the linear combinations of the A and B inputs. Then there's pairwise multiplication, and then there's additional linear operation represented by the W matrix, and this is the matrix representation of the same computation. So once Schwartz had that, everyone realized that if you can compute two matrices of some size n0 by n0 using only n0 by omega 0 multiplications, regardless of the number of linear operations, you can obtain recursively an algorithm with n to the omega 0 arithmetic cost. Order of that. And so here's a sample from the ongoing competition. And here's the thing. Starting from here on, the minimal applicable size of these so-called algorithms is larger than 10 to the 100. So larger than the number of particles in the observable universe.
I thought for Pan, that's not true.
So it goes up here. So Pan is applicable, and Bean is approximate algorithm. Once you exactify it, explodes, and then everything that use the tau theorem or the direct sum theorem, the laser method, these all explode.
Oh, I see. So the second Pan is using laser method, and the first one is not.
Right.
Actually, okay.
So this is the trilinear. This is the one that still uses the trilinear aggregation method. So in parallel to this computation, there's a computation on the best exponent omega naught you can obtain, where you can apply the algorithm to feasible size matrices. So Strassen had it for 2 by 2, then Ladderman for 3 by 3, albeit a bit worse exponent, and the computation goes on. And what do you need to provide when you show when you want to obtain such, to prove that you have such an algorithm? It's just the U, V, and W matrices, and since these are of bounded reasonable size, you can just write them down. Are these practical? So let's go into the constants. Pan's algorithm with exponent of about 2.773 has a hidden leading coefficient in the arithmetic cost of more than 700. That means that in order to outperform the cubic time algorithm, where the cubic time has arithmetic cost of 2 n cubed, we need to go to very, very large matrices. And the same goes with Smirnov's algorithm and with our recent trilinear-based algorithm. So this is a problem. Okay, so what do we need to do? Yeah, sorry.
In the previous slide, DeepMind is not a human, right? I'm pointing that out. So.
Right, so that DeepMind?
DeepMind is not a person.
Oh, that's true. Okay, so there's a very long list of authors.
AI
Yeah.
tool.
Yeah. Okay, so these two were obtained by I don't know, Deus ex machina. They just had the revelation. I don't know how. And Pan's algorithm. This is the trilinear aggregation method, which we reused. Smirnov used the alternative least square method. They used the Flipcraft's method, and DeepMind were one of several who that use the AI-based search. So either Alpha Tensor, Alpha Evolve, and others.
So,
Yep.
for comparison, what was the constant for Strassen?
Say again.
The constant for Strassen.
So I didn't hear.
What's the
So
constant for Strassen?
what the constant for Strassen is 7, and I'll go into that very soon. Okay, so this is the list we are looking at. So how to improve the exponent, the upper bound on omega, that we are doing in the more theoretical part of this workshop. And this represents what we need to do if we want to have actual practical fast matrix multiplication algorithms. So what do people do? One thing is they try to obtain fast matrix multiplication for feasible inputs. So the base case is of a reasonable size, and these are upper bounds, and then there are also lower bounds. Some of them are by people sitting here today. And then there's the research into what are the hidden constants, upper bound and lower bounds, and how can we improve them. Then if you want any of this to run fast in practice, what you actually need to worry is the communication cost. So you need to be communication avoiding, and I will almost not talk about that, and this is the next talk by Jim. and then you want to trust your result, so it needs to be numerically stable, at least to some extent, and how you make it more stable, if that is possible, and what are the lower bounds for that. And then there's another question, which is as follows. When you run in practice fast matrix multiplication, and that's a recursive algorithm, once your blocks get to sufficiently small size, you switch to the classical algorithm. Why? Because it's faster for smaller size. The asymptotic doesn't help you there. That's one reason. And the other reason is that vendors have tuned the heck out of it. So you want to do that. And then comes the question, is that as good as it gets? Or maybe there are alternative ways to compute the base case of the small box. And so there's research into that too.
So,
Yeah.
So if I get algorithm for say n by n matrix multiplication, I really have a 3 least square dimensional family as such. And so for all of these known ones, have people done searches over this sort of arbitrary changes of coordinates to see if they can make the constants better? Has that been done systematically?
So this will be the main focus of the talk. So I'll try to answer that in two slides. Yep.
Oh, great.
Yep.
Yeah.
Thank you. Yeah. We didn't talk. Yep. All right. So I'm not going to cover today this part, but I just want to mention. So trilinear aggregation method. This method of Victor Pans was the first to improve omega, so the theoretical upper bound on the tensor decomposition. So it was a decade of no improvement, and then he used that, but his method is also practical. So Victor will give a talk on that at the matrix multiplication workshop. And then the flip graph, that's a way of this search technique, Manuel will give a talk at the matrix multiplication workshop. And then there are other techniques like the alternative least square, SAT solvers, and zero padding, which we'll hear from Sedoglavic. And I'm not sure we'll have a talk about that. It's not clear yet on the AI-based search. OK. So my background is actually complexity theory. That's my education. And then I came to a visit here in Berkeley, and met with Jim and Olga, which changed my career and life. And then we had the first paper, which was on Cholesky, lower and upper bound communication cost. And the reviewer wrote something like, the low bound proof is easy once someone shows you what to do. And in a sense, this is going to be with us in this talk. So there are cases where proofs, once you are given like NP-like proofs. So once you're given the proof, that's very easy. You understand it quickly, and you can verify it quickly. And then there's everything that JM and Peter do, which even when you get the proof, it takes lots of time and effort, at least to me, to get it. OK. So if I get an algorithm, someone gives me provides the UVW representation of a Boolean algorithm, and in this case, this is Strassen's algorithm. How do I know that this is really a matrix multiplication algorithm? So I can apply, as Olga said, I can apply the test of Brent, the trilinear condition. So I take a column from U, a column from V, a column from W, do the equivalent of inner product, so multiply them in triplets, and then sum up the result. And then the result has to be either 0 or 1. If it's not, then I know it's not a matrix multiplication algorithm. And it's one if and only if the indices agree. So if I take a row from here, here, and here, a column from each of them, sorry, and the names of the columns correspond to the indices of the input and output matrices. So this is A11, A12, A21, A22, and the same goes for B and C. I take 3 columns, apply the trilinear test, the trilinear product condition, and I like to verify that, for example, if I take the first column, the trilinear product should be 1. But if I take the first, second, and last column, the inner product should be 0. So you have this and several other exercises in the homework assignment. And now I'll try to answer JM's question. Schwartz obtained a 7n to log base 2 of 7 arithmetic cost algorithm. And then a couple of years later, Vinograd improved this 7 to 6. And then there was a question, can we do better than that? And the answer is no. We have two proofs, 2 different techniques to prove that if you start with a 2x2 base case recursive matrix multiplication, then you require at least 15 additions. So 7 multiplication and 15 additions, which translates to a leading coefficient of 6. If you do the recursion, the master method, but you care about the constants, then you get 6 here. And then Eli Karstad, a student of mine, showed that you can do that with only 12 linear operations, which leads to a leading coefficient of 5. So what gives? What's happening here? So either they are wrong, or my student was wrong, which was my assumption to begin with, or math falls apart and the universe disappears. So it turns out that none of them is, and Probert and Pschuti had an assumption in their lower bound. And the assumption was that all computations in the bilinear algorithm are performed in the standard basis of matrices. So Eli noticed the following. You can, if you have an A and B input matrices, you can change their basis, then apply a bilinear algorithm, a UVW algorithm, which is not matrix multiplication. It computes something different. And then you can switch back to the original basis, combine all these operations, you obtain a matrix multiplication algorithm. And since this is not a matrix multiplication algorithm, then the lower bound of Probert, the lower bounds of Probert and Pschuti do not apply. But now you should be suspicious, because what is basis transformation? This is matrix multiplication. So what I just showed is that if you are willing to do 4 matrix multiplication algorithms, then one of them is cheaper. That doesn't make sense. But not all matrix multiplication were born equal. And we know that some matrix multiplication can be done very efficiently. For example, you can multiply with a diagonal matrix, or you can multiply by Hadamard transform, so Fourier matrix, very efficiently. And this is the case here. So these 3 transformation can be applied as fast as an FFT. So in time, which is only quasi-linear in the input size. And in effect, they look very much like an FFT matrix or a butterfly structure. Let me go just a little bit more deep. So here are 3 matrices that represent an 2 by 2 by 2 using 7 multiplications, fast matrix multiplication algorithm. What is the leading coefficient of that results here? So it depends on the number of linear operations of each of them. So the actual constant for applying the block multiplication, so that results into that where QU, QV, and QW are the number of linear operations that are given in the U, V, and W matrices. So the number of non-zeros, the number of non-singulars, so elements that are not 1, -1, and 0, minus the number of rows or columns. Okay. So what can you do? You can try and take out from the UVW matrices everything that is repeating, recurring, and do that part separately. So you take U and you express it as a U phi times phi matrix, where you want the U phi matrix to be as sparse as possible, and you don't care about the sparsity of phi, of the basis transformation. Again, you take U, you decompose it to a sparse matrix by invertible matrix. And you do the same for V and W. So this is how the base case arithmetic circuit looks like. When you apply this recursively, and this is the critical thing, you apply it in 4 distinct recursion trees. So you do all the basis transformation in one tree for the A matrix, separately for the B matrix. Then you apply a recursive tree on the bilinear algorithm, and then you apply the last transformation to obtain the C matrix. This way, all the recurring computation are done separately, and you apply minimal number of linear operations within the costly bilinear algorithm. Questions? All right. So now the next step was to look into all the zoo of algorithms for feasible input, feasible size matrices, and do this decomposition. So for each algorithm, decompose the UVW matrices to obtain faster algorithms in practice. Yep.
So if the algorithm uses complex coefficients, how do you count multiplication of complex numbers? Is that
right? So some of DeepMind's algorithms and other have coefficients which are complex, and then the question is how to count them. So I usually avoid complex numbers.
why?
Because they are complex and because they take longer to deal with. And so multiplying or adding 2 complex numbers takes either twice or 3 times the time of doing that with floating points. And therefore it's harder, if you get a UVW input which has complex number, it's harder to make it run faster in practice, but in some cases you can push all the complex number to the basis transformation, and then you pay the dear cost only with low exponents, and the bilinear part is cheaper.
So in general, finding a change of basis that makes it as sparse as possible, that must be a hard problem, right? I mean, that must be.
Yeah, that's an excellent question.
So, okay.
So it's not only NP hard, it's even NP hard to approximate. So it seems like a lost case. So
we're dealing with just doing this once.
Exactly. So we're doing it just once. It's not in runtime. It's in pre-processing. It's when you prepare the algorithm that you do that. And B, the sizes are reasonably small. And then you can use several techniques. You can either use brute force if it's very small. You can use any SAT solver of your choice. You can use all kind of approximation algorithms like the one of Gottlieb and Nylon. You can combine a SAT solver with Farkas lemma and several other techniques. And this is what we did in a series of papers. Okay, so what do we see here?
Finite fields or something.
Say again?
I mean, if you have an algorithm, you could just consider that over finite fields and then try to do the changes based
That's
on
what the
finite
Z3
fields.
solver does. It's exactly what the Z3 solver does.
That's F2 though, right?
Right. Right.
Is
So,
that ever F3 or F2? Because F2 is
You
like
can
a
also do
little
F3
special.
if you want.
it's a SAT solver, and so indeed some of the techniques both for basis transformation and for. Okay, let me reiterate that in a future slides.
Okay.
So, okay. Okay. So what do we see here? Let me focus on the first line. So the first column stands for the tensor decomposition, the algorithm. So this is Strassens. So 2 by 2 by 2, decomposed into 7 rank 1 or using 7 multiplications. And I'm sorry, it's a bit small. So the leading monomial is n to the log base 2 of 7. So about n to the 2.8. Originally, it had 18 additions. With the base change, we reduced that to 12. And that corresponds to about 28% of time saving. And so I promised to avoid communication avoiding issues, but let me just mention that everything here works also in the communication cost realm. So you reduce arithmetic cost, but you also reduce data movement within memory hierarchy and between processors. And this is Laddermann's algorithm, so 3 by 3 by 3 using 23 multiplications. So the exponent is log base 3 of 23. And it's a bit worse than Strassens. The leading coefficient used to be about 8. And using the basis transformation, we can reduce this to a bit less than 5.5. So 32% of actual time saving.
Now there's tons of these 3 by 3 and 23.
Right.
Is any of them better than Lederman?
Yes. So that's a very good question. And so we'll see that very soon. And this used to be the second best feasible algorithm. So this is Smirnov's algorithm, and there's a variant of it of Tikovsky and Kovac, where they use the base case of 6 by 3 by 3 using 40 multiplications instead of the classical requires how many? That was a question. Instead of 54 for the classical, right? 6 by 3 by 3. Okay, so 40 multiplications. The exponent is better than Strassens, it's about 2.77. And we reduced the leading coefficient from 55 to about 9. So this is a case where without the basis transformation, you could not actually run this algorithm, and with, you can, and it's actually reasonably fast.
Wait, Oded, this
Yeah.
is this is the asymptotic improvement as that goes higher.
Right. So the more recursive steps you can apply, the stronger you get the impact of reducing the cost. Yeah, exactly. Mm-hmm.
So those improvements, are those over the previous version of the same algorithm or over a baseline?
Those improvements are?
The improvements in the last column, they're over the previous versions of the same app?
The original.
Algorithm?
So we presented the way that present us the best. So we took the worst, like the original. So in the case of Strassens' algorithm, we compared to Strassens. Sorry. In the case of Strassens' algorithm, we compared to Strassens' algorithm and not to Vinograd's version of it. Does that answer that?
Yes.
Okay. Okay, does it run faster in practice? And the answer is yes. So what Noah, my grad student, showed is exactly that, the method of basis, of alternative basis, of basis changes, can be used in a way or can be implemented in a way that minimizes communication costs and reduces the communication costs by at least the same factor, and sometimes even you can show that it's even higher. And that means that regardless of whether the computation is communication bound or arithmetic bound, you get the expected speedup. Okay, and these are just a couple of examples. Here we compare, so x-axis is matrix dimension, log scale, y-axis is runtime, so low is good, and then we compare it to DGEM in Intel's math kernel library, and you can see that the speed up here approach about x2, and in this graph the y-axis is effective performance, so up is good, x-axis is the matrix dimension, and we compare to DGEM, to Strassen, and this is ours. And we have similar numbers on GPUs, and other people have implemented that. And addressing your question, so when Karpa and Kasky implemented GPU, their first step was to implement it for over Z2. So, and they found a basis, change of basis which is better than what we had, but worked only over Z2. And then later Noah extended it to work, so lifted it to work over arbitrary, so work over floating point arithmetic. Okay. So can we do better? So let me come back to the 3x3x3 algorithms. The classical algorithm requires about 2n cubed arithmetic cost. And then this is Ladderman's algorithm, but there are other with about the same leading coefficient. And using the alternative basis, we can reduce it from about 8 to about 5.5. Can we do better? So the first answer is no, and we had the lower bound proving that you cannot improve the alternative basis if what you want to do is reduce the number of linear operations. But then in a work with Gal Bignamini, we showed how to reduce it to 2. So let me first just focus your attention on that we get an algorithm which has the exponent of the fast matrix multiplication algorithms and the leading coefficient of the classical algorithm. So best of both worlds. And we did that for several other algorithms. This is a sample of them. So they reduced the leading coefficient to 2 from whatever it was originally and whatever was the best previous alternative basis.
Could you make a precise statement of the theorem?
Right.
The no part, I mean, the part I understand.
Yeah. So if you use alternative basis algorithm, then none of the 3x3 algorithm can be its linear number of linear operations can be reduced so that the leading coefficient becomes 2.
And how does the proof go? Because we don't know all the 3x3 algorithms.
That's a good point. So what do we need to obtain a 2? So there's a okay. Let me show the result, and that will explain what we assumed in the.
Okay.
So the algorithm looks almost the same with the algorithmic tool, with the exception that rather than changing a basis, we do the decomposition so that the transformation matrix is full rank. It doesn't have to be square. It can be rectangular. And so this opens the search space, and yeah, I'm not sure that this answers your question. So let's take it offline. This one. Okay, let me just. Oh, was it?
I mean, do you assume that you fix some algorithm and you just ask, what's the best alternative basis for it?
Yeah. What's the best decomposition? Yeah.
But there's some fixed initial algorithm, right?
Exactly.
Okay.
And in order to have leading coefficient 2, what you need is that you have repeating rows in your UVW matrices. So if you can prove you don't have them in a 3x3 algorithm, then that's a general a lower bound that you cannot do with an alternative basis algorithm. You cannot obtain a leading coefficient of 2. If you have at least 1, then with alternative basis you cannot, but with this one you can.
Can we again see the slide where you explain?
Yeah.
No, not the one where you yes. So this phi and psi, how these are not quadratic matrices, they are rectangular. That's what you say.
Right.
Still, you need full rank, otherwise you
Right.
lose too much information.
If they are not full rank, then you lose information. And
Yes.
so what you want here is a decomposition so that U, V, and W are as sparse as possible, and the transformation have to be full rank, but you don't care if they are sparse or not.
So you compute actually, in my language, you compute these linear forms. You actually compute more than, like if I compute
Yeah.
by 2, more than 7,
Yeah.
but they are so good somehow, so sparse, or I don't know, so it's worth doing it somehow.
Right. Right. So again, you will have four recursive trees, one for each transformation, and one for the bilinear portion of the algorithm. And what you can further do, since these are not n square log n costs, since these are not square matrices, then they have some lower degree polynomial costs. So say if this is n to the 2.7, then that would be n to the 2.3. So a polynomial degree that depends on the ratio between the input and output of these transformations. And so after you optimize for this part of your algorithm, these are as sparse as you want them to be, then you can repeat this optimization for the lower cost. And then you first optimize for the leading coefficient of your polynomial cost, and then you can optimize for the following coefficients. Yeah.
How big does n have to be for the first term to dominate the second term?
All right, too big. So, yeah. So, for example, for this particular algorithm, to outperform even the classical, but the Strassen's algorithm, it's in the 10,000s at least. There's another issue that if we do that, we increase the communication costs. And that is a problem, of course. And then there's open question of whether we can do both. Can we optimize the leading coefficient of the arithmetic cost without sacrificing the communication costs. And there are lower bounds and upper bounds on that, but this is an open question. So, yep.
You said before these sparse matrices are butterfly factors?
Not the sparse matrices, the application of the base change. Sorry. No. The application of this part of the computation looks very much like the application of FFT. So let me write down a couple of open questions. So the first one was, what is the best exponent for fast matrix multiplication on feasible size?
What's feasible these days?
Say again?
What's feasible these days?
Yeah. So what's feasible, that's not well defined, and that's also changes. So if,
These days.
yeah. So what's feasible size these days? I think for AI purposes, Gen AI, these are in the thousands. For the attention mechanisms, for simulation purposes and scientific computing purposes, we are already in the millions, I think.
Are
Well, it
they
depends.
unstructured matrices or because
Yeah, I'm not an expert on that, but maybe Jim knows.
They're often structured when they get that large.
so what's the largest unstructured these days?
Probably the impact benchmark.
I want a number.
Yeah.
Like 5,000,
Million.
10,000.
No, million.
Million.
Yeah, so the impact benchmark is this famous benchmark where all the supercomputers in the world compete with one another to see who's fastest, based on the NQ matrix multiplier.
I know.
But it's not a real workload, right? It's a benchmark.
Yeah, it's a benchmark.
What do people actually
That's why
do?
it's the largest. So,
I think you're not allowed to use fast matrix multiplication, are you?
They're not.
Yeah, I think you're not allowed.
Gray Ballard was really bitter about this.
Yeah. Yeah, I can relate to that.
One more thing about it. So you want the algorithm you want the algorithm to outperform the classic, for example, in the size of 10,000s or millions. But the base case algorithm must be much smaller in order to achieve that. So like 10 by 10 or 20 by 20 at most.
so I will have some performance data in my talk. So.
But I was just wondering, do we need something that's actually going to run better? Do we have the luxury of waiting till size 10,000 to declare victory, or do we have to start winning by size 2,000? Strauss starts winning.
The smaller the better, obviously.
Obviously, yeah.
Yeah, but Strauss's and essentially the alternative basis version of it wins the classical much sooner. So okay.
Quick question.
Yeah.
Can you comment on the stability of these methods?
I can if we have time, but let me just reiterate Olga's and Jim's comment on that, is that you cannot expect element-wise stability, but norm-wise you can, and there are several ways to either control or improve the stability. So diagonal scaling is one of them. You can utilize the alternative basis, so you can use the basis transformation to improve the properties of your algorithm at the same time. So they can be simultaneously used to improve stability and performance. can we obtain better fast matrix multiplication algorithms for low rank sparse or structured matrices. And in that context, let me remind a paper of Houston and Zwick, which showed how to take fast matrix multiplication algorithm with a sparse matrix multiplication algorithm and combine them into an algorithm that can gain both from the sparsity and the fastness of the algorithm. So if you just apply fast recursive matrix multiplication algorithm, you lose the sparsity very fast. If you just apply sparse, naive matrix multiplication, then you don't get any exponent benefit. So there are ways to combine both, but this is a paper for 2003. I'm not aware of any progress in this direction. What is the best leading coefficient you can obtain for various algorithms, and what is the best hope for small blocks multiplication.
What does that mean? Small blocks multiplication?
All right, so when you run a recursive algorithm, once you get to sufficiently small size, you switch to the classical algorithm. That's the standard. And the question is whether you can hope for something better, or is it always or almost always the case that classical algorithm there is optimal. So I have a few more minutes, right?
Yeah.
Okay.
Usually the base case is lower order terms.
Say again?
But usually the base case is lower order terms. So why optimize that part?
Okay, so the base case is lower order term, but in the recursive tree, it appears many times. So if you can save even just a constant factor there, then that has an impact on the entire runtime of your algorithm. So let me remind one work in this direction. This one. So the classical algorithm requires 8 multiplications and 4 additions. And Strassen reduced the number of multiplications to 7 while increasing it to the linear operations to 18. And then Karlstad showed 7 multiplication with, let's call it, amortized linear cost of 12, because there's also the low overhead of change of bases. And there's a question whether you can reduce both. What can you do in the context of trading multiplication for additions? And then Eli showed that 12 is the minimum number of additions you require if you do less than 8 multiplications. But then Yoav Moran showed that you can do 4 multiplications using only 8 additions.
I don't understand.
Yeah.
What can you do with 4 multiplications?
So what can you do with 4 multiplication? You can multiply 2 by 2 matrices using only 4 multiplication instead of 8 of the classical algorithm or 7 of the Strassen or alternative basis multiplication. So you only use 4 multiplications and 8 additions. But of course you cannot do that for a single 2 by 2 matrix. We have lower bounds on that. But what you can do, you can do that when these are blocks within a larger algorithms. So there's dependencies between those blocks of the recursive tree of the algorithm. So if you know that your algorithm is fast matrix multiplication algorithm with some properties, then you can utilize those properties so that each of the leaves in that tree, rather than using 8 multiplications and 4 addition, it uses 4 multiplications and 8 additions up to some amortized low overhead cost of the change of basis and corrections.
So is this the average cost per this 3?
So this is the average cost for each of the leaves of the 2 by 2 leaves of the tree.
So here you use, when you do the recursion, what you get, they become structured.
Right.
And you do something
To utilize that. Exactly. So the first to observe that was Vinogod, and he had a larger additional cost, a larger cost for a larger amortized cost, and we reduced that to a little of 1. Yep.
Where you stop the recursion?
Yes, it does. So if you stop at the recursion, of course, this is something you would not do in practice. You would not stop at 2 by 2. So this is not as so you can generalize that to B by B blocks, but then then this ratio is not as good. And let me just say that in general, this is so you have 12 arithmetic operations here and 12 arithmetic operations here, but in some cases, silicon dictates that multiplications are more expensive than additions, and so, or at least energy-wise, this can grow up to often x50 more expensive. All right. Okay. So lower bounds. Don't believe them. If you break free of some of the assumptions, then sometimes you can get better algorithms. But sometimes, as you'll see in Jim's talks, the low bounds can actually lead you to better algorithms. And open questions include improving the exponent for feasible input size, obtaining low bounds on those, improving the hidden coefficients, hidden constants in the algorithms, and obtaining lower bounds on those. Communication avoiding both lower bound and upper bounds, improving numerical stability, and obtaining better algorithms for the small blocks. One other thing that is of interest to me is to look into tools that we meet on the asymptotic study of omega, and try and think, where are they useful in practice? So one example is the restriction phase of the construction, where you apply linear transformation on the input and outputs. And this looked like a very theoretical tool, but as it happens, you can use very similar linear transformation to actually expedite, to make your algorithm run faster. Within the Schoenehage's paper on transforming from sparse to flag method to the dense matrix multiplication. So he manages to show a very useful, so preserve the number of useful multiplication. Can you do that in practice? What's the cost of transforming between sparse and dense multiplication? Okay, I think that's it. Thank you.
Oded, any more questions? Yes,
I'm just wondering about the methods that one has the impression, but I don't know whether it's true, that in order to find these new methods, you need a lot of computer search or optimization, or what do you actually do? I mean, is it maybe a combination of some idea, but there's a lot of, not things that you can do on a desk just with a pencil, and so you need a computer, right? Or is that correct, my view?
Well, it's true.
Computer scientist. You can do that. I can't.
So typically what happens is that for very small base case, or 2 by 2, 2 by 2 by 3 multiplication, then we do that manually. And this is like the first discovery. But then when you want to apply that to larger matrices, you have to use computer-aided search, and this could be SAT solvers and other tools. And in some cases, this is not good enough. For example, in algorithms that are based on the trilinear aggregation method of punts, the base case is about 40 by 40. That means that the U matrix is of size, of width 40 by 40, and of height, which is about 40 cubed. So 40 cubed divided by 2 point something. This is much too large to be, so that you will be able to apply SAT solver or other tools efficiently. And then for those algorithms, we use some analytic analysis. So we decompose them using their underlying structure. So we obtain the alternative basis decomposition just by using properties of the matrices.
Olga,
Can I take part of this question, please? You should talk to this wonderful undergraduate student, Abraham Huksu, who implemented all of this stuff on our most recent paper, who is, by the way, going to apply for grad schools. Just a little plug-in. He's totally amazing, and he can run this very fast now. So starting with, implementing this and letting the machine run for maybe a day or so. Now he can do all of this in absolutely, totally reasonable time, reasonable by human standards. So in 15 minutes, in 20 minutes, he can optimize your favorite, matrix multiplication algorithm, if it's of size, maybe 20 by 20 or something like that. So it's quite amazing what can be done. And this is not on a supercomputer. This is on a machine, which is comparable to your laptop.
So what?
No, he's here. He is a UC Berkeley student.
But not in the audience.
I was looking to see if he's in the audience, because then he could answer your question in great detail with but the code is in the paper. You can see.
Yeah, Yoav is here, and he also participates.
Yeah.
I know Yoav.
But this is only like with integers or something, right? Or over rational numbers? What? I mean,
The decomposition,
I just
or
don't understand how this. I understand how you can find something better. I don't understand how you can declare it's best. What you're searching.
well, you can sometimes. Okay, if you cannot do better than 2. So if you and this you can prove. And so if you obtain leading coefficient of 2, then it's the best. That's one. option. And another option is that some of these SAT algorithm, they guarantee optimal solution if they terminate.
So, can I?
Yeah.
So the algorithm we used in the paper was constructed in a way that always finds the optimal or one of the optimal decompositions, and it basically goes. Let's first find the sparsest vector we can get from the matrix, and then we'll just go a bit like relax the requirement a bit. So up to 2 operations, up to 3 operations, and so on, until we get the optimal composition.
But I don't even understand the definition of optimal. Is that just sparsity?
So JM, yes, sparsity
Exactly.
measures optimality, right?
Right, so then how do you-
we can achieve optimal, provably achieve optimal
So it's
sparsity.
optimal for a given.
But then how do you know that there's not some like really complicated coefficients?
Well,
complex coefficients
because we have a
that-
sparsity guarantee that we cannot go sparser than a certain amount.
Right, but that's not the machine. That's some other theory.
Right.
This is a theorem, yeah, this is a theorem.
Yeah. So okay.
And then we were lucky to get coefficients which are integer or, fractional of like a binary fraction type, but, yes, the sparsity provides a guarantee.
But the machine is finding the best thing for you, but there's a theorem that's telling you it's the
Absolutely.
best, not the machine.
Yeah, not the
That
machine,
was-
not
that
the
was
machine,
my mis-
absolutely. Yeah.
Okay, now.
And again, you have an lot about the implementation.
So, in the alternative basis test at the end, the follow-up, we can maybe interpret this as like we're finding a good basis for the which ring decompositions are very sparse. Like, is there, just as a qualitative question, do you have any sort of geometric insight about these alternative bases which are sort of seem especially good for low rank decomposition or sparse low rank decomposition? Or it was essentially just a list of numbers the computer spits out for us for.
Yeah, I don't think I have a geometric interpretation of the. I don't have, in general, I don't have geometric interpretations. So, yeah, sorry.
Yes.
Do you know the fixed size matrix you can do less arithmetic operations than the naive algorithm? Like, is that even possible? Because the general Strassen, you have 15 extra or something like this.
Fixed size where you
Fix
have.
the size n by n,
Yeah.
and then look over all algorithms. Are there any that use less flops than naive would?
Almost all of them. So take Strassen's algorithm and take a few recursive steps of it and fix that as your base case, and then it uses less operations than the classical algorithms.
I'm not talking
algorithm.
about recursion.
Okay.
So without recursion, if you don't use alternative basis, then there is a proof that you can't do better.
Okay.
But with alternative basis, we don't have a proof.
Okay.
Any idea that how these algorithms, I suspect they are currently implementing software. Any idea how they can be extended to, if you can also change the hardware as well? Like many people are doing this nowadays.
Right. So without stealing any of Jim's talk, so one problem that we have with okay, so we utilize it when we implement those algorithms on existing hardware. We utilize all accelerators that are available. So Tensor Core, AMX, and similar. Thing is that these are very well tuned for the classical algorithm. So if we had the freedom to change the hardware, then there would be certainly some things that we would like to do, like changing the trading computation for communication. So I would like to be able to change that in favor of my sweet point of the sweet point for those algorithms. That's one thing. The other thing is that interprocessor, intercore communication networks are typically grid-like, so 2D, 3D grid. This is very good for classical matrix multiplication. This is not good for Strassen and other fast matrix multiplication algorithms. So if we had the freedom to do that, then we would change the on silicon. Yeah.
There was a talk in the hardware boot camp last week
Right.
about people building three-dimensional chips so you can have tighter interconnects.
Right, which are perfect for 2D, 2.5D, 3D algorithms, but as we proved in the paper with Jim and Olga, they do better for fast matrix multiplication algorithm, but still you have contention. So they are not perfect for Strassen and other algorithms. And if we had the freedom to do whatever network we want there, then there are much better ones. Yeah.
So real networks are built to deal with contention in interesting ways these days. So for example, what they will typically do to send a message from one processor to another is send it to a random intermediate processor and then to the final destination to avoid congestion.
Right.
But just this sounds a little maybe pessimistic. Just to maybe make a counterpoint, if you want to design a new chip for a small power of 2 and use these methods, be our guest. So we would love to talk to you.
You're saying it's
doable. It's doable.
It's known that there are ways to design hardware that make Strassen better than the naive algorithm.
You can do it.
It has just
You can do it. Yeah.
it's not been
doable.
done for other reasons. That's accurate.
The problem sizes have to be large enough that the market isn't there, I think.
So even the 2000 by 2000, like somebody was saying, Strassen is better for 2000, but that's not the threshold at which these would be better.
Well, you do Strassen and then at the base case switch to the what the accelerator does.
The improvement on the alternative basis method. Actually, do you mind going back to the slide where we discuss the? I think going down to 2. I'm curious about the cost of because it sounds
the 2
like
by 2.
The
first
one after the pure alternative basis method. I guess I'm curious about the runtime.
Which one?
I guess okay. My question is about the runtime of this. So alternate basis, we pick a good basis, and then new insight, we can pick a good like inclusion into like a larger space, right? Like we embed C4 into C5 or something, right? So it seems like we might incur a cost when we do this embedding because we're now dealing with larger objects. So is that,
you're talking about the second technique.
yeah, the one after the alternate basis method.
The rectangular matrices.
This one. Yeah. And so let's look on the table. So this is what you're referring to.
Yes.
So the 6.75 and to the log base 3 of 21. So it's not a quasi-linear, it's actual additional polynomial cost with lower exponents than the original algorithm, but still significant.
That's a cost.
And then we have ways to optimize this. So
that
reduce either omit as many monomials as you can, and once you did that, reduce the coefficient of each monomial as far as you can, but still you get an extra non-trivial cost.
So that 21 is occurring as the embedding size of the.
Exactly.
Okay.
Exactly. Yeah, and this is where the additional communication cost comes from. So from applying this, from the communication cost of this part of the algorithm.
So speaking of numerical stability, what's the range of numbers that you get as in the coefficients in that step, in the alternative basis?
So in many cases,
plus minus 1.
Yeah, in many cases these are plus minus ones, but not in all cases. If the original, many of the basis algorithms actually have very few elements. So they're either 1, -1, and zeros, or as in the case of the Smirnov and Tikovsky-Kovac 33640 algorithm, they also have 1/2 and -1/2, 1/8, and 1 minus that. Yeah. but not
Yes.
yeah, but not all of them. Some of the algorithms that AlphaEvolve found have complex numbers, but then people found versions of them that do not, that have only few real values. So that's good. Yeah.
So, like on your first slide, you talked about two things, which was like computational time and also energy cost.
Right.
And it sounds like it's harder to get. It's hard to beat the benchmark naive application, except for very large sizes, in terms of computational time. But is the crossover point lower if we just care about reducing energy cost? Like,
Yeah.
we
So
might not care about.
yeah. So let me just repeat that. So what about the energy cost of these and similar algorithms? And there's a good reason for that. So new data centers suffer from not enough power, and they build nuclear power plants next to data centers, and they need lots of water and cooling. That's a real problem. And when each new GPU requires 1,200 kilowatts, that's hot. And so maybe in some cases, since we reduce computation cost, but more importantly, we reduce communication cost, maybe even if we don't outperform the usual gem, time-wise, maybe we can save energy costs. And
I will talk about that a little bit.
Okay, so I'm done.
Okay, thanks.
Okay.